Okay, just 2 minutes later, it's a good thing, no? Because usually we always start 5 or 10 minutes after the beginning. But anyhow, it's a pleasure to introduce to you Federico Rodriguez-Hertz from Penn State, and he will be talking about the bounded cohomology and the dynamics.
Thank you very much, Cece, and thank you very much for the invitation and the opportunity to celebrate Marcelo's birthday. So I want just to make a little anecdote about my interactions with Marcelo, or more important interaction with Marcelo is how Marcelo make a huge interaction in my career. So several people, I thought everyone here knew I was graduated from IMPA, but it seems that not everyone knows it. So I was graduated from IMPA. And this anecdote is how I arrived to IMPA. So I was stuck in '96 in Uruguay. I was not allowed to study in the university. And I'm from Argentina originally. So there was no way back for me because I didn't want to go back. And there was no future in Uruguay. So I got stuck there until, well, Marcelo essentially produced the opportunity to come here to study and make my PhD at IMPA. So thank you, Marcelo, and really was a wonderful experience. I had the opportunity to share with, well, all the people that have been mentioned in this conference. And it was a great environment and, well, very fruitful. Okay, so let me start with the talk. And so it's about bounded cohomology, and dynamics. So I'm mostly a dynamicist, not a topologist. So this bounded cohomology is something that I was always curious because it was almost impossible to understand what it's the definition and what it is. And it appeared, I saw it appear naturally in several problems, and I wanted to understand what it is. And well, I just started playing with it, and I made my understanding what it is, which is, I would say, essentially the joint of the understanding of people doing bounded cohomology, but anyways, it's my understanding. So first thing, so I will spend some time in defining what is bounded cohomology and then switch into dynamics as I go. So same way there is bounded cohomology, there is something that I like to call unbounded cohomology, which for me is a little bit more understandable. But that's not a standard name. I think the most standard name is quasi-cohomology, but even that is not very standard. So, so let me just put some setting here. You take a group gamma, and you define these cohomology groups, say values in R, where it's something about co-cycles being co-boundary or not being co-boundary. You can go to Wikipedia and just put group cohomology, and it gives you the definition of the delta operator and do the stuff. So as I said, it's not important for us really, this part of the game. And you can put subscript bounded here. And now I want to be a little bit more specific. So you take some guy, which will be real valued, and you want it to be closed. And this guy without the b will ask whether this guy is exact or is not exact. Now, the main difference with bounded against unbounded is the space of functions C you start with. So you have first state of functions, which is all C into R. So this is, let me call it C2, just to put some notation. So this will be all possible ones you could imagine. Then gamma is discrete group, so here is no topology in the group. Or you can take C2 bounded, which is all this is gamma times gamma into R, such that the L infinity norm of C is finite, so it's uniformly bounded guys. And then if you start with this guy, you get this. If you start with this guy, you put a subscript bounded there. Okay, and makes the huge difference, the whole difference.
What is delta? So
Delta is the derivative operator. It's the exterior derivative. It's Wikipedia in your phone, and group cohomology is C of blah, 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 minus blah, 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 plus blah, blah, blah. Some alternated sum of some operations. It's incomprehensible. Well, not for people doing cohomology, of course. So I'm just talking about me. Sorry for the people doing cohomology. I'm saying these type of things. OK, now, of course, when you are looking at the kernel, also, you want to be the delta of a bounded guy, OK? When you do the quotient, you want to preserve. Now, you could define yet another space, which would be C2 unbounded, which is just C2 divided by the bounded ones. So you are really looking to the unbounded piece of the world. So this will, in turns, actually, well, I put a subscript 2, the same you can do with C1 unbounded, and all other levels. And then when you play a little bit with this group, so you have all these sort of universal coefficients and exact sequences, it turns out essentially that the H2 bounded of gamma is nothing but the H1 of gamma unbounded, essentially direct sum. So probably, I'm not sure, I think you don't need to make any further assumptions. But it's pretty much, this comes from an exact sequence. So it's not sure about the sum, but you sandwich the guy in between two things. So you get this. So which means that this is standard group cohomology. People know what to do about this. This is the incomprehensible guy. So you translate this into an H1 incomprehensible guy. Okay? Now, what type of group we are thinking here? Gamma is pi 1 as a surface, compact surface. So it's a little bit more general than that, but this is certainly the D group we care about. So then this is just R, is, well, connected surface, so it is just R, so is this the guy. So not much to say. And so let me describe then what is this, which is very easy to describe now. So it's something I can understand. So, and these are what is called quasimorphisms. And now I can give the formula. So you have function C, maybe call it L, from gamma to R, which does L of gamma 1, gamma 2, minus L gamma 1, minus L gamma 2. This is delta L at gamma 1, gamma 2. So here I even have formula for the delta. And you ask for the guy to be bounded. So this is a quasimorphism. So is this guy's norm? Well, L infinity, yeah, I put L infinity more, so it's correct. So this is the absolute value of this expression, supremum over all possible gamma 1s, gamma 2. You want to be uniformly bounded. So if you get this being equal to 0, this is exactly the homomorphism from gamma to R, which is the H1 of your system. Okay? But you may have a lot of guys. So let me give you a somewhat different context of group, but one of the most famous quasimorphisms in dynamics, which is rotation number. So it's completely out from the type of guys I'm going to discuss, but it's a good example. So you have the homeos of the circle. You have to take the universal covering because actually I want the lift of them, not really the guys from the circle. And you define this as a mapping to R. So this is rho of F is rotation number. And then you just follow the proof, and you see that rho of F compose G minus rho F minus rho G is less than or equal to 1, if I'm not mistaken. So this gives you uniform boundness, and this is a quasimorphism. And that's very helpful now if you understand this guy, or equivalently you understand this guy, and you want to embed your group gamma into homeos, and if you know quasimorphisms are trivial, or you know something about quasimorphism, you will know something about the rotation number of your guys. And this always gives you a lot of information. Okay, so that's one of the uses. So I think that the most important use for this business, and actually they were created, if I'm not mistaken, by Gromov, is to understand the coarse geometry of the groups, or actually, you don't only do it for groups, you do it for spaces, and then it's the coarse geometry of the spaces. So this type of object is able to understand the coarse geometries, meaning that if you have two spaces which are quasi-isometric, then their H2 or HK boundaries should be essentially the same. And so then you can start distinguishing, and that's typical Gromov type of problems he likes. Okay. Exactly. If you take a subgroup of rotation of the homeos, so we are looking for group actions on the circle, then you consider a subgroup of homeos, then you restrict the rotation number to this subgroup. This gives you a quasimorphism of your group. Then if you know that this group is trivial, for example, then you will know that the rotation number now on this group is a homomorphism. And that's a lot of information. Because then, well, you can just F compose G, and the rotation number will be exactly additive. Eh? Pretty much. So you can, yeah, you start playing with that, and pretty much you end up, or it's fully 0, and then all the guys are rotation number 0, so you only have fixed points. And again, then you gain a lot of information as well. So that's the type of game you play. Okay, one more thing I wanted to say. Yes, of course, the most important thing is it happens. So everything here is with Pablo Carrasco, of course. He's in University of Minas, Federal of Minas Gerais. So everything. So nothing here is out of Pablo Carrasco. Okay. So as I said, the main object of study here so far will be this fundamental group of compact surfaces, but actually everything I'm going to say is should be as well true if you just assume this group gamma is hyperbolic, Gromov hyperbolic, or I don't know, they have several ways of saying, modifying the word hyperbolic, but they are all hyperbolic. So what we really care about this is some consequence of the hyperbolicity, which has to do with dynamics, which is like the most important thing for us about the fundamental group of a surface is that there is a geodesic flow coming on the unit tangent bundle to the surface when you put a metric of curvature -1. And here you also will have some sort of geodesic flow on some geodesic space, over some geodesic space, and that's all the same type of hyperbolic dynamics we know that happens for the geodesic flow. That's really what we care about the group, but that's exactly what are the hyperbolic groups at the end of the day. Okay? Okay, so now let me say epsilon about the little history I know about this, because bounded cohomology is really a huge subject, and even restricted to the thing I'm going to discuss is still a huge subject, and I know very little about it. So if, to the best of my knowledge, the first person which computed to some extent this guy, so let gamma be the fundamental group of a compact surface, then the dimension of H2 bounded gamma R is infinite. So this group have infinite dimensions. It's not something finite where you typically like to play with cohomology with some finite vector space or finite dimensional vector space. So here is all the way infinity. So then there is a second proof of the same result, but a somewhat different construction, which is by Brooks and series, which is a little bit more dynamical, and in a sense, it's very much in the spirit I'm going to discuss later. Then comes a work by Epstein and Fujiwara, which again, so then this was for surfaces. They, if I'm not mistaken, go all the way to hyperbolic groups to prove always the same claim. And it's very important for what I'm interested, not just the proof of this is infinite dimensional, but how to produce the linearly independent, infinitely many linearly independent guys. So that's how they produce these quasimorphisms or these cohomology classes. Then finally, in the list I'm discussing, comes Ursula Hammenstadt, who also proved dimension is infinity for hyperbolic groups. Well, first for surface groups, I think in the same paper she also does a lot of things about bounded cohomology, but she produced the examples of quasimorphisms I want to discuss. And I forgot one more in the list, which is important as well, which is here in between, which is Barsh and Gis as well. Build a very nice and geometric thing, which is somewhat related to this, but also somewhat related to assumption generalization. I don't think I will have to discuss, but I think it's still important for the type of things I'm doing. OK, so let me now finally show you that this dimension is infinity. OK? So take your surface, take the unit tangent bundle to your surface, consider, just put the metric of curvature -1 on this. So now this is the tangent bundle. You have the orthodesic flow G sub T. Now take Helder functions, this space of Helder functions. I will have to quotient, but I will quotient later by some quotient of this space, which still be infinite dimensional. And I will assume this function phi. Let me write a little bit grotesquely, but is symmetric, so minus. It's an odd function with respect to this V guy. I will give you also some explicit examples of this which are of interest. So now you define L of gamma. Gamma is an element in the pi1 of the surface. You define as the integral over gamma of phi on G of T dx, if you want, from 0 to the length of gamma dt, x and point in gamma. Well, in the periodic point, periodic orbit homotopic to gamma. So P of gamma, homotopy class is, and here is not just homotopy class, is homotopy class is conjugated to gamma. Okay, so given any homotopy class, there is one and only one geodesic which is conjugate to this element of the group. Of course, if the element is the identity, you define it as 0, so you don't care. Other than that, you just define it as that. So naturally, by definition, one may start being suspicious, if you want, that L of eta, gamma, eta inverse is gamma, because if I'm just conjugating, I'm giving the same number. Also, you will get that L of gamma to the n is n times L of gamma. Here you see, if I'm moving +1 or -1, I'm supposed to switch signs, and that's why I'm asking what I'm asking about the function phi. And here, of course, you have to be coherent, and if you are taking gamma to the n, then the periodic orbit is the one that just goes n times along the very guy. So, but then you just define this. This seems a little bit suspicious, like some triviality, but then you can show easily that any quasimorphism is cohomologous to one satisfying that, just by some general nonsense. So then there is not any more suspicious. So that's how they work at the end of the day. OK, so you have this, you just define this, and then you have to show that this is a quasimorphism. So you have to bound this, but this is integral gamma 1, gamma 2, minus integral gamma 1, minus integral gamma 2. OK, so now is where you have essentially to work a little bit, but essentially what you are saying is, I have my periodic orbit gamma 1, I have my periodic orbit gamma 2, and I have gamma 1, gamma 2, which is essentially the specification orbit. So it goes around here, and then it goes and goes around here, and then it closes. And then you use a specification. So the first piece of this will be shadowed by this piece. The second piece of this will be shadowed by this piece. And what is left is uniformly bounded. So for this to happen, you just need the function to be Hölder so that specification works. So works when you apply it to a Hölder function, and you defined your bounded, your quasimorphism. So you have to argue that when you take gamma 1, gamma 2, and then you take gamma 1 times gamma 2, so it's a little bit more complicated than what I just drew, but essentially what you are doing is a specification property. You are looking for the periodic orbit which shadows the first one and then shadows the second one. This gamma 1 dot to gamma 2 is in the fundamental group, so it's the product of the two elements of the fundamental group. So it's the concatenation of the loops. But then you argue, there is a lot of technicalities here to discuss, but that's pretty much why it is true. And essentially, the proof is you write one page with all the epsilon deltas, finding the point, this and that. And that's it. And yeah, there is, so this again will appear there because of what I said about conjugating, because actually when I do a specification, I'm not doing gamma 1, gamma 2, I'm doing eta gamma 1, eta inverse gamma 2, and then I have to cancel whoever was one direction and the other. Several details, but morally is that. So this way, for every element here, essentially you build an element here. Now you want injectivity. So you want just to prove that this guy is injective. So let's prove the guy is injective. So what's the problem? The problem will be integral of phi. The gamma is less than a constant. That's essentially the issue. You will have a bounded quasimorphism. So that pretty much will be the point. But then for every gamma, so over gamma, that's for every gamma. Here, just let me emphasize, these integrals I'm writing is not normalized measure on the periodic orbit. So the integral of the function 1 will be the length of the orbit. So this is not bounded. So now imagine you have this uniformly bounded. Then I start iterating here. And this is uniformly bounded. So at the end of the day, you get that this has to be 0. So saying that this is bounded is the same as saying that this is 0 for every curve. And then you know Lipschitz theorem. This implies phi equals to Lx u. So this is Lipschitz equation. So you can solve this equation, which means that the kernel of this guy is this. So you quotient by the kernel, these co-boundaries. And now you have this space. This is a Banach space, thanks to Lipschitz. And it's an infinite dimensional that you can show simply by playing with periodic orbits. Once again, I'm making it not trivial or periodic orbit. And you are embedding this one-to-one fashion into these guys. So you get infinite dimensions. Okay? Now, what we want to do is to show that this is onto. Now, there is an issue to show this is onto, especially about the alpha. So you can show that actually there are functions which are not homologous to beta regularity. So you really have to put the union over all alpha positive here, and still it's well-defined object. So you have now it's not anymore a Banach space, it's an ugly space from the analysis point of view, and pray for this to be onto. And no, it will not be onto. So we will discuss why, but it will not be onto. And I really want something on this side which, from the dynamical point of view, I can understand and be able to say this is an isomorphism. So that's what the question is. So what type of functions should I look for if I want this? And then what the type of functions is the following. So it's, as always, the functions that make the work work. So it's Bowen property. It's something that Bowen defined in the 70s, even before Gromov defined his group, something that Rouel has been working quite a bit, probably next off it from Gromov, but for some reason they didn't give Gromov the answer. So what is the Bowen property? It says the following: function phi, M, remember, is the unit tangent bundle, has the Bowen property. If for every x, y, and t, let me put this way, quantifiers, if there exists epsilon positive and z positive, then if I do the integral between 0 and t, phi gtx minus phi gty, even if it is repeating, I want to put separate. This is less than c if distance from gtx to gty is smaller than epsilon for every t in the interval 0 t. So if 2 points stay together for the first t times, that's said that point x is in the Bowen ball of point y, then their Birkhoff average, well, not the average, the Birkhoff's integral between 0 and t stay uniformly bounded. So Hölder functions do that because this will imply that the points x and y have to start exponentially close in the unstable direction, and doesn't matter much the stable direction. And the Hölder property will allow you to compare these things, and this is not a plus minus, this is a t minus. So then you put these together and you get the integrability. So this property actually was the one used when you come here, you have the two periodic orbits, the points are in the same Bowen ball, you have uniform bounded, so you have the Bowen property, and then just, again, you work epsilon more, and then you can put these functions with the Bowen property over there. And now you extend to something, and what we prove with Pablo is that you quotient this by coboundaries, and now this is an isomorphism, and it's a Banach, in a sense, isomorphism. So if I put the natural norm here, natural norm there, they do whatever they have to do. There is one subtlety that I'm not saying. I didn't say anything about the regularity of the function phi, other than this. I'm not going to have continuous functions. I have to give up continuous functions. I will assume here in this space is contained in L infinity of measure of maximal entropy. Or actually, for that matter, I choose my favorite equilibrium measure with respect to a Helder potential, and I can put it there as well. So any such will give me essentially the same. But since I can only define them almost everywhere, I have to make my choice of reference measure. And I'm choosing the measure of maximal entropy because it's the measure of maximal entropy. I could use Liouville as well. If someone thinks that Liouville is better than MME, you choose MME. But
What is the natural norm of this bound function?
and this Bowen function is the optimal C and the L plus the L infinity norm. Or plus the L1 norm or something, because the Bowen norm is already almost dominating whatever. You just need to have a point or something where you have not the guy going to infinity. Okay, so the Bowen norm is a semi-norm. It's just the constant, which is the problem. So you have to make sure the constants are not doing anything. But other than that, you are happy. So Ruel and Haydn, and Ruel himself, played quite a bit with these guys without assuming continuity. But then they still assume it was defined everywhere. And it's not obvious, at least not for me. Maybe it's true, but I was not able to prove it. And it's not necessary, on the other hand, to show that if you have a function defined almost everywhere, so here I have to then be a little bit more precise. Then I will ask for this to happen, and then the points x and y will have to belong to the domain of the phi. And I will ask the domain of phi to be an invariant set. And then you still want to do this same thing. Then there is a subtlety. So here it's full of subtleties. So I have to give up the function to be defined everywhere. But then I'm evaluating it over a periodic orbit. So you say periodic orbits are not seen by MME. The good news, and this already was done by Haydn and Ruel, is that you can define a functional L sub phi from the space of invariant measures into R, which will be a continuous functional, and that's the integral. And the way you do it is by taking the Birkhoff average and showing that it has to be convergent, so on any place. So, or somewhat equivalent way, you approximate these finite integrals by continuous functions. The error will be uniformly bounded. So you have for every t, and L sub t, this is convergent, so this is a very well-defined object. So you can really do all the standard theory with Perron-Frobenius and blah, blah, blah with this space. So it is a very, actually, you don't need even this be measure 1. You could even assume it's just a dense set. Any dense set would do, and you can develop the theory. Actually, we can show with Pablo that if you start with a phi on a dense set, then there will be another guy which has the same integral of periodic points with the same Bowen property, but is defined almost everywhere with respect to MME or whatever reference measure you are willing to do. So it's very flexible. So, so yeah, the theorem, let me state it at the end of the day. So it's good to have a theorem which says hypothesis, thesis. If not, there is some schools that don't like it. So I'm just restating it. It's just for the records, the lawful part of the game. This is in one-to-one correspondence, and this, let me put sub odd. So odd means phi of b is the same as minus phi of minus b. This is in one-to-one correspondence of this. Okay, so can I see from here? I cannot see. 237. Okay, I'm not so bad. Okay, so maybe I should say epsilon about the proof of this. So you just do Perron-Frobenius, but you do exactly, completely the opposite way. So Perron-Frobenius, typically you are given a potential, then you give an equilibrium measure associated to the potential, then you even go and study statistical properties of this equilibrium measure and say a lot of things. Here, zeta function, which actually in a sense will appear here. Here you move exactly the opposite direction. So I will have this quasimorphism. There will be some sort of zeta function or something of this sort. Then there will be an equilibrium measure, and then you want to get the potential, which will have this equilibrium measure. And then you even have to work a little bit more, because I want the function defined not with respect to an equilibrium measure that depends on the function, but MME. So then one have to play even a little bit more, but that's OK. So let me give you, since this is just a sketch and very sketchy, so let me not put all details. So you go and define the pressure of your guy, L, in the obvious way. It will be, OK, first reduction. I will not write the proof in this setting. Let me just do first reduction. Let me just give you the sketch of the proof in a simplified setting. Shift on two symbols. Now, quasimorphism means that when you concatenate two words, this stays uniformly bounded. Okay, this L goes from the alphabet into R. That's the meaning of quasimorphism in this setting. OK, so then this is the setting I will show a sketch of the proof. So I will build a potential associated with L. And this potential will have the Bowen property and will be defined almost everywhere with respect to someone. Then we can go even and show that the Perron-Frobenius, we cannot show a spectral gap for the Perron-Frobenius. Ruel and Hayden also weren't able to show any spectral gap for this Perron-Frobenius. Even what we can prove in this respect better than Ruel and Hayden, we can show that one is an isolated eigenvalue. So for the Perron-Frobenius. So this is what that's part of the game as well for the last part. But let me start. So you define the pressure of L. This is sum with words of the alphabet to the power n, e to the L of omega. Then you take a logarithm, you divide by n. And actually, let me call it, without this, let me call it Cn of L this. And then the P of L is limit 1 over n log of Cn L. OK, so that's the pressure. And you show that the limit exists. You have all the sort of subadditivity or almost subadditivity that will make life work. So really, life is very benign for this part of the theory, so you have to suffer much later. So it's very satisfactory when you see that the trivial thing works. So it never happens, but sometimes you are lucky. So then you just define this sequence of measures, mu n, which is sum 1 over Cn, sum e to the L omega delta omega, omega in the alphabet an. And again, you suffer, but you end up showing that mu n L is convergent to some limit. And in showing that this is convergent, actually, the way you do it is by showing that these mu L n's are very well behaved with respect to intersection of cylinders. This is less than a constant, larger than 1 over a constant. Of course, this needs quantifier, so the n has to be much larger than the size of the cylinders. And then the constancy is very specifically, explicitly computed. It depends on the norm of the quasimorphism. So, and then you control. Then this will mean that any accumulation point of this will be ergodic. And maybe I forgot. Wait a second. Yeah, I want to shift one of the guys, I think. So they have to be sigma k, and the b is smaller than the a, so but sigma minus k. But anyway, so in the limit you will get essentially that all measures. So the measures in the limit cannot be. So any accumulation point will be mixing, and also any accumulation point will be, or at least ergodic, and will not be singular. And so if they are ergodic and non-singular, it is unique. So that's how you get, but also you get nice control on the limit. Okay, so that's the first thing. Then the second thing you do is you just write down what one is supposed to know, what is the potential if you know the measure. So you just divide this by this, mu L of the sheaf of the X, this cylinder has size n minus 1. You take a log here, and you show that this is conversion. Actually, you show that this is some sort of martingale, super martingale, sub-martingale, some sort of martingale, and you show that this is conversion almost everywhere to some limit, and that's the guy. And this guy will have all the regularity because you build it to have all this regularity, and when you integrate this phi with respect to any measure will be the same as that L of guy there. So it will give you the same answer than this functional I saw. So in particular, periodic orbit is that's the same, and you recover what you wanted. Now, as I said, there is a slight issue here. This almost everywhere with respect to the measure mu. The measure mu is not the entropy maximizing measure. It's a measure that it has a nice property, but it's not what you wanted. So next step is to suffer. Essentially, you do some explicit computation, but this explicit computation comes from analyzing the following. You take now a parameter S in the interval 0, 1. You take your potential phi naught, Helder. You have this L phi naught, which is the quasimorphism which integrates for this phi naught. And you now take S times L plus L sub phi naught. This is a quasimorphism, as well as before. So this will produce, by this construction, in phi S. And then you essentially take the ds at s equal to 0. So you have to show that this exists. So it's like differentiating martingales, but well, in this case, we were able to show that this essentially makes sense, give you a guy, and this exists is a phi, which is defined almost everywhere with respect to the equilibrium measure of phi naught. So in particular, I could put 0 here, and then it will be everywhere with respect to the MME. Okay? So that's, in a summary, what I wanted to say. And I think I consume all the time, so I'm sorry. That's it. Thanks.
Thanks. And please, are there any questions or comments? Okay. If not,
Oh, there is.
More about the bound cohomology. So
yes.
If I recall correctly, there's this other definition of group cohomology where you build this huge space and it's just the singular cohomology of that.
Yeah, you can do bounded homology of spaces.
Right.
And you define it pretty much the same way I said, but then you use the chain complex for the space and with bounded or not bounded things. And yeah, actually you do the L1 homology using simplices, and then the bounded will be the dual of L1 homology of the space. Simply because the dual of L1 is an infinity, so then the dual of L1 homology of the space will be this. And here, essentially, what you are looking is, when you have a group gamma, you look at the space where the gamma acts co-compactly and in a way that you can quotient and have a nice compact space. And then one can show, I think it's not hard to show that it's exactly the same groups you are talking about.
Thanks.
More questions? Okay, then let's thank them.